Bismillah ar-Rahman ar-Rahim. We have two interesting limits. Let's start with the first one. We have summation k from 1 to n, 1 over n plus k to the x. We are interested in taking the limit as n tends to infinity. X is a parameter. Specifically, x is a positive real number. So this is the limit. And let's assume first that x is strictly greater than 1. I will write the sum as summation k from 1 to infinity, 1 over n plus k to the power x. And then I will put here indicator that k is less than or equal to n. So this is equal to 1 if k is less than or equal to n, 0 if k is greater than n. So we have the limit as n tends to infinity of this infinite sum of 1 over n plus k to the x, indicator k less than or equal to n. Now let's investigate the magnitude of the summand. So what we are summing can be upper bounded by the following. The indicator function is 1 or 0, so it is upper bounded by 1. 1 over n plus k to the power x. Now this is less than or equal to 1 over k to the power x. So we have an upper bound, which is 1 over k to the power x. Now, if we try to sum the upper bound, summation k from 1 to infinity, 1 over k to the x, this is a convergent sum when x is strictly greater than 1. So this is a finite quantity. So we have a summand. The magnitude of the summand is upper bounded by 1 over k to the x. And here we don't have n, the variable with respect to which we are taking the limit. And 1 over k to the x, when we sum, gives us some finite number. This means we can apply the dominated convergence theorem and we can take the limit inside. So this is equal to summation k from 1 to infinity. And then we take the limit as n tends to infinity, 1 over n plus k to the x. And then we have the indicator of k less than or equal to n. The meaning now is that for a given k, we take the limit first and then we do the sum. Now, if we fix k, then this indicator will tend to 1 as n tends to infinity, because for any given k, as n increases, sooner or later n will overtake k, and this indicator will be equal to 1. So this will go to 1 as n goes to infinity. What about this one? As n goes to infinity, this will go to 0. And so the product is 0. This is summation k from 1 to infinity of 0, and this is 0. The limit here is equal to 0 if the real number x is strictly greater than 1. But in our problem, x is any positive real number, so we still need to consider the cases in which x is 1, or perhaps it is strictly less than 1. It is between 0 and 1. If x is equal to 1, then our limit becomes limit n tends to infinity, summation k from 1 to n, 1 over n plus k to the x. Now it becomes k to the power 1. What we can do now is that we can take n as a common factor. So this is limit n tends to infinity, 1 over n, summation k from 1 to n, and this will be 1 plus k over n. And this looks very much like a Riemann sum. So we have a delta, which is 1 over n, and it goes to 0 as n goes to infinity. This is integral k over n. This, as n tends to infinity, this is from 0 to 1. 1 over 1 plus v dv. This will be this integration written as a Riemann sum. This integral is len 1 plus v. And if we use the integration limits, this will give us len 2. The last case, if x is in the open interval between 0 and 1. Let's take the summation k from 1 to n, 1 over n plus k to the power x. Let's try to upper bound and lower bound. Okay, so let me write this again, k from 1 to n, 1 over n plus k to the power x. Now this is less than or equal to summation k from 1 to the n, 1 over 1 plus 1. The minimum value of this term k to the power x is 1. So if we replace k to the x by 1, then we have an upper bound. And then we have the summation. Note that the summand now becomes independent of k. We basically have a constant, and we are summing this constant n times. So this is equal to this constant 1 over n plus 1 times n. And this goes to 1 as n tends to infinity. Let's try to lower bound. So in the upper bounding case, k is replaced by its smallest value, which is 1. Now, if we want to lower bound, perhaps we need to replace k by its largest possible value, which is n. So summation k from 1 to n, 1 over n plus k to the x is greater than or equal to summation k from 1 to n, 1 over n plus n to the power x. Same thing like above. We have a summand now that does not depend on k. And so the result is basically this term here multiplied by n. So this is n over n plus n to the power x. And note that x is a number that is between 0 and 1. So here, if we divide the numerator and denominator by n, we have 1 over 1 plus 1 over n to the power 1 minus x. This is a positive power. So as n gets very large, this will tend to 0. And again, we approach or tend to 1 as n tends to infinity. So the upper and lower bounds both tend to 1 as n tends to infinity. So the limit is equal to 1. Now we can summarize our results. We have x is strictly positive, real number. The limit as n tends to infinity, summation k from 1 to n, 1 over n plus k to the power x. We have three cases. The first one, in which we have employed the dominated convergence theorem. If x is strictly greater than 1, we got 0. Now, if x is exactly equal to 1, then we got a Riemann sum, and the limit is the natural logarithm of 2. If x is between 0 and 1, then using the sandwich theorem, the limit is equal to 1. Now let's investigate the second limit. The second limit is related to this summation here. This is the sum of the positive integers 1 to the power 1 plus 2 to the power 2 plus 3 to the power 3 all the way to n to the power n. We are interested in the limit as n tends to infinity of the nth root of this summation all the way to Vn, where V is some positive integer. This is divided by n to the power alpha, and alpha is a positive real number. Before proceeding, let's think more about this summation here, and let's try to have bounds on it. So the idea is that we will try to upper bound and lower bound this term here, and hopefully we will get to the same limit. In other words, we will try to apply the sandwich theorem, but this will require that we have good bounds on S of n. So what can be those good bounds? Consider the function g of alpha, which is 1 minus 1 over alpha to the power alpha. And let's take alpha to be greater than or equal to 2. So alpha is a real number that is 2 or more. We show that this function is strictly increasing. G of alpha is equal to e to the power alpha log 1 minus 1 over alpha. And if we compute the first derivative is e to the alpha log 1 minus 1 over alpha. And then we take the derivative of this product. So this will give us log 1 minus 1 over alpha plus alpha. And then if we differentiate this, we get 1 over 1 minus 1 over alpha. And then we need to differentiate by the chain rule, minus 1 over alpha. This gives us 1 over alpha squared. Simplifying, we have e to the alpha log 1 minus 1 over alpha, and then log 1 minus 1 over alpha plus 1 over, from here we get alpha minus 1. We want to show that this first derivative is strictly positive, indicating that our function here is strictly increasing. And so the way to go is that we will make use of this inequality log of beta, where beta is a positive real number. So beta lives in the set of positive real numbers, is less than or equal to beta plus 1. Okay, and this inequality can also be checked using standard calculus techniques. If this inequality is true, then log 1 over beta is less than or equal to 1 over beta minus 1. Just replace beta by 1 over beta. If this inequality is true for any real positive number, then the reciprocal of a real positive number is another real positive number. So log 1 over beta must be less than or equal to 1 over beta minus 1. Note that this inequality here is satisfied with the strict equality if and only if beta is equal to 1. So we have equality if and only if beta is equal to 1. Now, log 1 over beta is minus log beta, and this is less than or equal to 1 over beta minus 1. Multiply both sides by minus 1, and so the inequality is reversed. What does this mean? Now, go back here, replace beta by 1 minus 1 over alpha. So according to this inequality, log 1 minus 1 over alpha is superior to 1 minus 1 over beta, and so I should write here in the denominator 1 minus 1 over alpha. Multiply upstairs and downstairs by alpha, so this becomes 1 minus alpha over alpha minus 1, and so this is alpha minus 1 minus alpha over alpha minus 1. This is minus 1 over alpha minus 1. Now move this to the other side. Log 1 minus 1 over alpha plus 1 over alpha minus 1 is strictly greater than 0. And why strictly greater than 0? Because we have equality if and only if beta is equal to 1. Note that we replaced beta by 1 minus 1 over alpha. And 1 minus 1 over alpha is never equal to 1 because alpha is a real number that is equal to 2 or more. So because of this, indeed, our inequality is a strict inequality. If we go back to the function g, it has this bracket here, and this is strictly positive. The exponential is strictly positive, and so the first derivative of this function is strictly positive. Now our conclusion is that the function g of alpha, which is 1 minus 1 over alpha to the power alpha, is strictly increasing on this interval here. And so g of alpha is greater than or equal to what is the minimum possible value? The minimum possible value is when alpha is equal to 2. And this function keeps increasing, and it is less than or equal to the limit alpha tends to infinity of 1 minus 1 over alpha to the power alpha. So the lower bound is 1 minus half, that's 1/2 squared, so 1/4. And this limit is e to the minus 1. So our function g of alpha is between 1/4 and e to the minus 1. This is a preparation so that we can bound the sum 1 to the 1 plus 2 to the 2 plus 3 to the 3 and so on. Let's use this to study the ratio n minus 1 to the power n minus 1 over n to the power n. Note that in the summation of interest, n minus 1 to the power n minus 1 will be the term before last, and the last term will be n to the power n. So we are investigating the ratio of these two terms here. N minus 1 to the power n minus 1, this is 1 over n minus 1 to the power n divided by n to the power n. Here, n is an integer that is greater than or equal to 2. So this is equal to 1 over n minus 1. Now these two guys will give 1 minus 1 over n to the power n. This is the function g applied to n. Now we can say that this ratio, n minus 1 to the n minus 1 over n to the n, this is upper bounded by e to the minus 1 over n minus 1, because this is less than or equal to e to the minus 1 by our previous result. This ratio is lower bounded by 1/4 times 1 over n minus 1. Again, because g of alpha, which is 1 minus 1 over alpha to the alpha, is greater than or equal to 1/4. So keep this in mind. This is a very important inequality. N minus n to the power n minus 1 over n to the power n. This is between 1/4 times 1 over n minus 1 and is upper bounded by e to the minus 1 over n minus 1. Let's go back to our summation. Our summation is Sn, which is summation k from 1 to n, k to the power k, which is 1 to the 1 plus 2 to the 2 plus n minus 1 to the power n minus 1 plus n to the n. Definitely this summation is greater than n to the n. N to the n is just one term in this summation. Now we can upper bound each term here by n to the n. And so this summation is strictly less than n times n to the n. This is n to the power n plus 1. So s to the n is upper bounded by n to the power n plus 1. And to get this upper bound, we just replace each term by the biggest term, which is n to the power n. So we have that s of n is less than or equal to n to the power n plus 1. So s of n minus 1 is strictly less than, so just replace n by n minus 1, n minus 1 to the power n minus 1 plus 1. And so this is n minus 1 to the power n. And we can do a further step of upper bounding and say that Sn minus 1 is less than n to the power n. So we upper bound n minus 1 by n. Sn minus 1, which is this summation here all the way to this term, is less than or equal to n to the power n. Let's go back to Sn. Sn is Sn minus 1, which is the sum of all those terms, plus n to the power n. We have just shown that Sn minus 1 is less than n to the power n. So this is less than n to the power n plus n to the power n. And this is 2n to the power n. So now we have a result that Sn is less than 2 to the n to the power n. If we apply this result to Sn minus 1, so replace n by n minus 1, Sn minus 1 is less than 2, n minus 1 to the power n minus 1. Now go back to Sn. Sn is equal to Sn minus 1 plus n to the power n. Now let's use our more refined upper bound. So this is less than 2 times n minus 1 to the power n minus 1 plus n to the power n. We can use our inequality here. We can take n to the power n as a common factor. And then we have 1 plus 2 n minus 1 to the power n minus 1 over n to the n. This is the ratio that we have previously investigated. So this is less than or equal to n to the n, 1 plus, let's go and copy the upper bound. So the upper bound is e to the minus 1 over n minus 1. So the upper bound here 2 to the e minus 1 over n minus 1. That's an upper bound on S of n. We have progressively refined an upper bound on Sn. We started by saying that Sn is less than or equal to the summation of Sn with each term replaced by the biggest one, n to the power n. And so we obtain the upper bound n to the power n plus 1. We applied this upper bound to Sn minus 1 by replacing n by n minus 1, and then we did further upper bounding by saying that n minus 1 to the n is less than n to the n. Then Sn is Sn minus 1 plus n to the n, but Sn minus 1 is less than n to the n. So Sn itself is less than 2 n to the power n. We took this upper bound and applied it to Sn minus 1 by replacing n by n minus 1. Again, we went back to Sn is equal to Sn minus 1 plus n to the n. Now, this Sn minus 1 is upper bounded by 2 n minus 1 to the power n minus 1. Then we have taken n to the n as a common factor, and we used our previous result, which gives an upper bound on this ratio, n minus 1 to the power n minus 1 over n to the n. So this is what we need as an upper bound for Sn. The lower bound is more straightforward. Sn is equal to Sn minus 1 plus n to the power n. Now, Sn minus 1 can be lower bounded by its biggest term alone. So this is strictly superior to n minus 1 to the power n minus 1 plus n to the power n. We can take n to the power n as a common factor, and we are left with 1 plus n minus 1 to the n minus 1 over n to the n. We know a lower bound on this ratio here. The lower bound is 1 over 4 times 1 over n minus 1. So we have this inequality that Sn, which is summation k from 1 to n, k to the power k. This is less than or equal to n to the n, 1 plus 2e to the power minus 1 over n minus 1, and is greater than or equal to n to the n, 1 plus 1/4 over n minus 1. Now we are in a position to attack our problem. Our problem involves Svn. So it is the summation over the positive integers all the way to Vn. No problem. We just replace this n by Vn. So Vn to the power Vn, 1 plus 2e minus 1 over Vn minus 1. And here we will do the same, replace n by Vn. Then we need the nth root of Svn. And so we need to raise the terms here to the power 1 over n, Vn to the power v. Then we have 1 plus 2e minus 1, Vn minus 1 to the power 1 over n. And on the left-hand side, we also have Vn to the power v times 1 plus 1/4 over Vn minus 1 to the power 1 over n. The problem wants the limit of Svn to the power 1 over n, the nth root of Svn, when we divide it by n to the power alpha. And alpha is a positive real number. The relevant term here will be n to the v minus alpha. Those brackets are innocent. Basically, as n tends to infinity, the inside of the bracket will go to 1 and the power will go to 0. So those brackets will tend to 1 as n tends to infinity. The important term is n to the v minus alpha. And from here, we can write down the result of our limit n tends to infinity, s of Vn to the power 1 over n to the alpha. This is, if alpha is less than v, then the lower bound will explode to infinity as n goes to infinity. And so the limit will be plus infinity. So plus infinity if alpha is less than v. If alpha is greater than v, then the upper bound will be n to a negative power. As n tends to infinity, the upper bound will go to 0. And this is a non-negative quantity. And so the limit will be equal to 0. Finally, if we have v is equal to alpha, then we have n to the 0, which is 1. And the remaining term is v to the v. And this will be the limit, v to the power v.